All right, so our last review period, if you will, for today. I did want to go over just briefly and somewhat. I'm very much trying to parallel the textbook in terms of stuff. It may be a bit different, but one thing they're very methodical about this. I'm not as methodical, but I really think it's good just to have a general strategy. So they give you this acronym GRASP, which is a way to approach problems and say, okay, what am I given? Right. So just list all the information that you're given. V1 equals this, A equals, whatever. What's required? So list the variable you actually want to find. Do your analysis, which basically would be looking, if you go back to what we just did with the big five, figure out which equation can I use? How can I figure out that unknown given what I do know? Solve, actually do it, and then a problem statement at the end. I would even add into that, like, interpret the result, make sure you've answered the question. I always say that on tests and things like that. Always reread the question, make sure you actually answered it. And some things that have already come up, and I feel like they're really, really keys to solving physics problems, is look at each dimension independently. All right, we saw last time, if you're given an acceleration, you can break that into its x and y components, and you can analyze each dimension by itself. Um, and this second one was a little bit what I just mentioned, right? Analyze your answer to see if it makes sense, and then reread the question. But yeah, definitely interpret your results, right? Do these numbers make sense? And probably a part of that is even consider, before you even answer your question, just give it a thought, like, what sort of number, what do I expect here? Right? And so if you get something way outside that range or in the opposite direction or something, you can go back and sort of reanalyze, how that happened. Were you wrong initially, or was there some problem with your calculation? One thing that can help if it's conceptual, that's this one I wrote right here. Consider extreme cases, right? And that's a big thing in physics. I find is consider, like, if you're really trying to figure out how something works or if something has an effect, you can consider stuff like that. I'll give you a little bit of a physics example then to consider extreme cases. So, um, you're in a little, could be a pool. Let's say you're in a pool. It's water. It's summer. You're after class, whatever. You're sitting in the pool, and you're on a little raft in the boat, and there's you on the raft. I don't pretend to be an artist, and you've got yourself a little block, right? Little brick or block or something like that. You throw the block into the water. Does the water level go up or down or stay the same? And yeah, a lot of people would say up. Don't forget I'm just older, hence the gray hair. But I remember a lot. That's one of the things I loved about physics. Learning it was, being wrong and figuring out concepts. Anyway, you throw the brick over, and it's kind of hard to even just look at it. Not because it's a bad picture, but because it's a weird problem. And so this was one I always remember because it was one where extreme examples kind of help. So think of it this way: would the water level go up or down? Well, we know that the brick or whatever we're throwing in is more dense than the water. So consider something really, really extreme. Let's suppose instead of it being a brick, it was like a little piece of neutron star or something like that, right? Something ridiculously dense, like it takes up almost no space at all, but it is very, very massive, right? Has the mass of a house or something, right? What's going to happen while that little thing is sitting in the boat, right? Well, the boat is going to be down, or the raft is going to be down very far, which will mean the water level is a little bit higher. Once you throw that out and it goes to the bottom of the pool, right? Well, it doesn't take up any space or practically no space in the pool. But what's going to happen now that this raft isn't so heavy, right? It's not going to be pushing down so hard, which means it'll go up, which means the water level will actually go down, right? Because now you don't have this massive raft down so far into the water, it can go up. So it's not displacing as much water, right? So it's just one of those examples I remember for anytime you get something like that and the question seems a bit different or odd or you can't be quite sure, try to think of really extreme examples, right? What if the mass was really heavy, or, what if the speed was really, really fast or really, really slow? And just think of how that would impact or what it might do. One other thing I'll give you, these are sort of the two strategies I've always kept. I don't pretend to be the best problem solver in the world, but there are two. One is, what do I need? And this one is actually, sometimes I kind of call this like work backwards, right? And I think there was a lot of forces problems. I remember grade 11 that were like that, where maybe you have like an astronaut with a certain mass pushes an other astronaut, and you want to figure out the final speed of the second astronaut or something, right? And so you're told the time of contact or whatever, right? So you kind of have to work your way backwards and say, well, what do I need to calculate the second astronaut's final velocity, right? Well, I need the acceleration. How do I get that? Well, I need the force. How do I get that? Well, that's Newton's third law, and whatever force, the first astronaut exerts on the second exerts on the first, right? And so you just keep working your way backwards. That sometimes can be helpful. The other one, and don't underestimate this, what can I do? And this is like, maybe roughly brute force, which is like you look at a problem you've got, it's asking for something, you're like, I don't know, but just ask yourself, what can I do? What can I calculate, right? Even if you go back to this grasp or whatever, what am I given? Like, what's required? And if you're thinking, I have no idea how to get what's required, but just look at what you're given and ask, is there something I can do? Is there something I could solve for? And sometimes that leads to something else. Sometimes once you get that answer, you start to put some of the pieces together, and then you think, oh, now I could calculate this. It's maybe still not what I want, but so it's, those are my general strategies. I feel like they're helpful. And I always say, don't be afraid of brute force. Sometimes we want solutions to be really beautiful and elegant and all that, but that just comes from lots and lots of practice, and sometimes it comes from something that is very brute force, and just reducing it down and refining it. So anyway, the range equation, I think they give you that in the textbook. My opinion is, don't do it. You can write it down if you really want, but for most of the problems we do, it's actually not that helpful. It's very limited. It requires that you're at the same height. So the idea with the range equation is you've got some, let's say this is ground level, and you have some projectile, right, that goes like, you shoot some, right, and you just want to know the range. How far does it go in the x direction? So it's very dependent on this, and often we're not necessarily going to have the same height that it starts or finishes at. So I would just say, do a more careful analysis of everything you're given. And for the time this would save once in a blue moon, I just, it's not worth it. I think we can do better. All right, so let's look at an example. We have a divorced man throws his wedding ring off a bridge with an initial velocity of 40 meters per second, 30 degrees above the horizontal. The bridge is 80 meters above the water, so we want to determine how long until the ring hits the water, and the horizontal distance covered, and then the final velocity at the ring's maximum height, and the final velocity, which would be when it hits the water. So already the range equation or anything like that is no good, because it starts at a height 80 meters above where it lands, right? So I think you can kind of picture this. You could diagram it out if you kind of wanted to. You could say, well, let's just look at where it starts. I guess first I do try to always say, here's my positive x direction, here's my positive y, and I'll just let this be. I'll just do a little, ideally north, south, east, west, but just a little origin thing or here or whatever, and say, okay, it starts 40 meters per second, so this will be, this will be v1 is 40 meters per second, and we know that this angle here is 30 degrees. All right, so right away we can break this up into components, which I assume is what I'm going to need to do. Particularly, yeah, I can already look at A, and I can say, let's just look here in the y direction. This thing starts out at a certain height with a certain velocity, right? So here's the bridge, and it's going to start going up with some. I'm not sure what's happening to my. It won't draw. All right, there we go. So we have some V1 in the Y direction, which I actually don't know right now, but if I'm just looking at the Y direction, it's going to go up, and then I've got the water here. So this thing is going to go up to some maximum height, and then it's going to come all the way down and hit the water, right? So one of the really neat things with problems like this is, I've mentioned before a number of times now, I know it, you can analyze each dimension independently. But the real question, even for something like this, is does one affect the other? Does it matter at all that it's thrown at this angle of or when it's thrown at an angle of 30 degrees, there's some, like, let's call this v1y, and there's some v1x, right? Some component to this in each dimension. Say I figure out what this is here. Does it matter what this is? Does it matter what v1x is when I'm looking at v1y and I'm trying to do some analysis down here? Does that matter at all? Yeah, and absolutely the answer is no, right? It doesn't, for all intents and purposes. There might be some extreme cases, but really no, right? It doesn't matter at all. You can look at it completely independently. Go back to that one I gave you earlier, that question about the astronauts way out in space and one goes to the left, right? If they're both moving forward with the same speed and then one goes right, the fact that they have this forward velocity doesn't matter at all. Similarly here, it's hard to really get a good perspective on this, but it's almost like, imagine you're far away from this whole situation. You're standing way, way, way over here, and you're looking at this happen, and you don't have any depth perception. Let's say you can't really see that this thing is being thrown somehow like this. You can't really see that. All you can see is it's going up and down. Maybe there's even some sort of screen in front of you or something, right? You can't perceive how it's x direction velocity at all, right? As far as you're concerned, as far as you can see through this screen that only lets you see if it's going up and down, this situation is exactly the same as if this guy threw his wedding ring straight up with V1Y, right? And it just goes up to whatever maximum point, and then it goes right back down, right? And that is exactly what happens. The fact that it also has an x component to its velocity doesn't matter at all. It just means it is going to move in the x direction. But as far as how fast this thing, as far as its velocity in the y direction, doesn't matter at all. Only gravity matters for that, because that's what's going to affect it, right? So in our analysis, we can look at V1Y, and as far as we're concerned, this guy just threw this thing straight up with V1Y. which I guess means we should figure out what V1y is. Right? In this case, V1y, well, the sine of 30 degrees would be V1y over 40. So you multiply that through and say that's going to be 40 times by the sine of 30 degrees. Sine of 30, we've seen it before. We know it's a half, but yeah. For V1x then is going to be the complement of that, right? We could say the cosine of 30 is going to be V1x over 40. So this is going to be 40 cosine 30 degrees. Okay. We can work out these numbers. Again, sine of 30 degrees is a half. So we can say, well, that's just equal to 20. And cos of 30 is root 2 over 3. So we can say that's works out to be 34.6, I think, if we want an actual number. So now that we're looking at this problem in just the y direction, we can say, look, it's got V1y, if you want, is 20 degrees. Now remember, up is positive. Remember our coordinate system, that's always important here. So it starts by going up 20 degrees. What else do we know? Well, we know the acceleration is negative 9.8 because we've said that up is positive. We know the displacement, right? We know it starts out at a height of 80. So if we assume that this point here is 0 where it starts, right? Assume up at the top of the bridge here where it starts is 0. Its final position, D, which I guess technically is a vector, the way I'm doing it is negative 80. And what do we actually want? I want to know how long. So I want the time. So to figure this out, now this is one of those things where even in grade 12, a lot of people, you kind of want to break this into two parts, right? How long does this take to get to the top? And you might say, well, I could calculate this, right? I could calculate how long until it gets to its maximum height, right? Till it reaches a speed of 0. Then I could calculate how long from until it gets to that maximum height until it goes all the way back down. Here's one of the really, really awesome things with these equations and why having a sign convention in these equations is so important, right? Because I just said D is negative 80, right? It starts going positive, right? Positive 20 is its initial velocity. So all of that stuff is built into the equation. So if you want to look at an equation, well, what equation do I want to use? I want the equation without V final. So that means I want D equals V1t plus 1 half AT squared. That's the equation I want. That will give me time. All of that stuff is built in. So I just have to use this equation once, putting all this information in here, right? So the distance is negative 80. V1 is positive 20. Time is what I want. Plus, now you could do it, doesn't matter. You could put plus 1 half. The acceleration is negative 9.8 t squared. And you can see now I have one equation with one unknown, time. And this will actually give me the total time to go up to its maximum height and all the way back down. Like I said, it's built right into it. I just have to actually solve this thing now. So 1 half of negative, so this here is negative 4.9. So I would move that over to the other side so that it becomes positive. So I'd have 4.9 t squared minus 20. So I'm putting everything over on the left side of this equation. Minus 20t minus 80 equals 0. Now how do I solve this? Absolutely, right? This is the quadratic formula. Right? So negative b, which in this case is positive 20, plus or minus the square root of b squared. 20 squared would be 400 minus 4 times a times by c. And c is negative 80, so that just makes that a positive. All over 2a. Well, a is 4.9 and 2a, as you all know, is 9.8. And that will give me the time. Substituting these numbers in, we get t equals 6.57. And we get negative 2.49. This second one, of course, we will dismiss and say this is inadmissible. Right? Because we don't want the negative time. This just means if you were to graph this function or something like that, that would also be one of the zeros, but it's negative. Or I sometimes like to think of the physical interpretation if I wanted to. Suppose this problem had been changed so that instead of starting here, suppose the guy had thrown it, he was on a raft in the water and he had thrown it so it goes like that, right? This negative 2.49 would be how many seconds before it got to 80 meters was it, right? Did he throw it or something like that? So it does have like a meaning, right? It's not nothing, but for our purposes, it's inadmissible. But anyway, for our purposes, we now have the answer to part A, right? How long until the ring hits the water? And again, we didn't need the X direction at all for this part, right? It takes 6.5 seconds to hit the water. So now we can look at part B, the horizontal distance covered. Right? So now we need to look in the X direction. And now we have to look at like, well, what do these two things have in common, right? The X direction and the Y. And the only thing they really have in common here is the time, right? The time that this thing is in the air is the same, right? And we now know that this thing takes 6.57 seconds until it hits the water, in which case it stops moving in this way. And if you were to look at the components of the velocity again, the x component of the velocity is unchanged, right? This is a very, very important point with projectile motion. That remains absolutely constant, right? If there was a bird flying above this whole situation or something like that, looking down, um, and if that bird was flying with a constant speed of 34.6 meters per second, as far as the bird is concerned, right, the ring would just be going up and down, right? The bird wouldn't see it moving back and forth at all because it would have the exact same constant speed or velocity, whatever, that the ring has, right? So it would only see it move up and down or get closer to it, then fall back down. So this remains absolutely constant. So we can use the fact that the v is constant, and that means we just know that d in the x direction is just v in the x direction times by the time. That's all we need. We don't need any of those big five equations because those are for acceleration. You could use them and put in zero, but you don't need to. You could just go back to the fact that v equals d over t, rearrange that for distance, and you get this. And that means that the distance in the x direction is 34.6 times by 6.57, which means the total distance in the x direction is 227.5 meters. It's a pretty good distance. I guess this divorcee was really upset when he threw it. It happens. C, the velocity at the ring's maximum height. Right. When it gets to its absolute maximum height, what has to be the case? I'm seeing people write this down, which I agree with, at max height. But this is just missing something, right? Vy equals 0. Remember, we could look at this y direction completely independently and say, yeah, when it reaches its maximum height, of course, v is 0. But Vx is constant, and we just said that's equal to 34.6. Thus, at its maximum height, it still has the x component of the velocity. But yeah, this is a big, this is a big thing to really understand, that v in this case is 34.6, right? Because the y component is 0, but the x component of the velocity doesn't change, right? It's still moving sideways, if you will, or in the x direction with this. This never changes. And I'll write in there meters per second horizontal, just because, yeah, this is really important to understand exactly what's happening, right? That it doesn't stop moving there. Okay, we got one more thing, and I think it might have a little bit of work to it, but what are we asking for? The velocity. Just making sure parts see the velocity at its maximum height. Okay, that's what we did. Now we want the final velocity. Okay. Um, if we want to get the final velocity, again, we need both components of the final velocity, right? We need to know how fast is it moving in the x direction, how fast is it moving in the y direction. X direction is nice, that doesn't change, so we already know that. But we don't know v2 in the y direction, right? So we can kind of go back to our equations up here. Remember, we looked at the up here, we looked at the y direction. We know the acceleration is constant. We know the displacement. We already found the time. So we can kind of pick and choose which equations we want. I think I use the one v2, we'll call it v2x equals v1x plus at. Find that one pretty, simple or straightforward. Subbing in the numbers here, and again, be very careful with. Sorry, I just realized I made a silly mistake. I think we're looking in the y direction. X we're pretty good with. And so that means v2y equals v1y, which we said was 20, positive 20, plus negative 9.8 times by the time, which we said was 6.57. And that means v2y equals negative 44.4. Just plugging in the numbers. So now we know the components of the final velocity, because again, x doesn't change. So that means v final is something, I'll sketch it a little bit like this. I don't know why I'm making it so big, but we'll call this v2 or v final. And we know the x component is the unchanged one, which is 34.6. And now we know y is negative. This is 44.4. So now we just need to figure out the magnitude and direction. And once again, as we've done multiple times, we're going to have to do some trigonometry here. Good old, to get the magnitude of v2, we're going to have to use Pythagorean theorem, and that tells us that that is going to be equal to 34.6 squared plus 44.4 squared. And if we plug in those numbers, we get 56.3. Then we can figure out the angle. Hold on. The angle here is So I'll make the angle this one right here. Now I have to be careful I understand what this angle is, right? So this is going to be below the horizontal. And then I can just figure this out. Tan theta